Okay, so for today, for analysis of algorithms, our goal here is for you to be able to describe algorithms, to see how to write and understand pseudocode conventions, and how do we actually measure algorithm runtime. Okay, so before we proceed with the actual analysis of algorithms, let's go back to our definitions again. Okay, so for algorithms, again, it's a well-defined computational procedure which transforms our computational problem, our inputs, into the desired outputs. Okay, so the goal here is to achieve, of course, our desired output, and that's the task. That's the task that we are looking for when accomplishing, uh, when we want to make these instructions. Okay, so a correct algorithm stops at the correct output for every input instance. But there's another criteria here where we talk about good algorithm. So it should be a good algorithm should be a correct algorithm, okay? But it also solves a problem at a reasonable amount of time. Okay, so it's the same way like if I ask you to look for let's say look for a person on Facebook, but instead of using the search bar, I want you to collect all the users on Facebook and search all of them one by one. Okay, so if I ask you to do that, that's almost impossible. Okay, I mean it's possible if you are still uh awake when you're still searching for that person, right? So it's nearly impossible because it would take so much time for you to do that. You just imagine how many users are on Facebook already. And then I ask you to do that, diba? So wala na. So a good algorithm would solve that problem, okay, at a reasonable amount of time. So how do we define how do we know if it will be solved at a reasonable amount of time? Okay, it's by looking at the algorithm runtime. Okay, so the algorithm runtime, it's a measurement of performance of the algorithm, but it's not exactly the same as program runtime. Okay, so I'm not sure if you have encountered it before on your programming classes where you put a timer at the start of the program and set another timer at the end of the program, and then you subtract the start at the end. You subtract the start from the end, and you see the program runtime. Okay, that may be an indicator, but it's not exactly the same as algorithm runtime, because in algorithm runtime we are not talking about seconds anymore. We are talking about very generic unit of time. So if the computer uses milliseconds, that will be applicable to milliseconds. If the computer or a machine uses hours, maybe, then that will be applicable to hours. So it's a more, generic abstracted level of runtime. Okay, so before we go down into algorithm runtime, let's revisit our binary arithmetic. Okay, so isa-isahin ulit natin, what should we do here? Okay, so we need to look at the leftmost bits, okay, and then we add them. So 1 plus 0 will be 1. Okay, now we move to the next to the left. So it's 1 plus 1 equals 0, 1. So 0 here, and we carry over 1. Okay, 1 plus 0 is 1, and 1 plus 1 is 1, 0. So again, the same thing. And then 1 plus 1 is 1, 0. Okay? Wala naman tayong problem dun, no? So same naman. Same process as before. Okay, so if we try to write down the instructions here, okay, we could say that we first look at the rightmost bits and then add them. Once we add them, we record the sum. Okay, now we move to the next bits to the left. Okay, and write the overflow bits, if any. Okay, hindi tayo nag-overwrite here because it's simply 0 from 1. But in that case, you can still overwrite or write the overflow bit 0. Okay, just to be formal with the rest of the bits. Okay, so we add 0 and then we proceed with the same calculation. So look at those bits. Okay, record the sum, move to the next bit to the left, and write the overflow bits, if any. Okay, so far so good. Wala namang question. Okay, so still the same binary addition that we did previously. So now if we try to formalize this, okay, so into set of instructions. First, we have an input. We have two binary numbers, A and B. Okay. Now we also have an output, okay, which is the binary number, one binary number for A plus B. Okay. And the procedure here, we just write them down, yung kayo as arrows natin. Okay. So it's the same thing, exactly the same thing as the previous slide. Now this is now your set of instructions. And if you show it to maybe to one of your classmates here, they would recall how it's being done because the present ko na yung visual form. Okay. Probably sometime in the future, you would remember that slide na, yes, this is the correct binary addition because we first look at the rightmost bits, we add them, we write the sum, we move, and then so on, blah, blah, blah. Okay. Now, but the problem here is that for machines, okay, they don't actually understand these instructions. Okay. First of all, for them, what exactly is a binary number? Okay. And how do they point to the rightmost bits? Okay. Where is left and right basically from their in their thinking, if they have. Okay. What are bits even? Okay, parang ganun. So in this case, even programming languages wouldn't understand them right away. Okay, so we need to go down to a lower level of language for our programming languages to understand these instructions. Okay, so what if I convert this? Okay, instead of saying we have two binary numbers, let's say we have two n-bit binary integers. So the length is defined. Okay, it's an n-bit stored in two n-element array. So now we are giving some representation of the binary integers. Instead of throwing it away now, we have two numbers. Let's say that we have two n-element arrays, okay, that represents the n-bit binary integers, okay? And the element array is composed of zeros and ones, okay? So now it's more clear. It's clear for our computers to understand because they know what an array is. They know what the length of the array they need to allocate, and they know what elements are inside those arrays. Okay, so we have two n-bit binary integers stored in two n-element array of zeros and ones. Okay, while our output would be a n+1 element array C of zeros and ones such that C is equal to A plus B. Okay, so we define an element of n+1 length, or an array of n+1 length, okay, such that the values here would be the same as A plus B, or adding the two n-element arrays in our input. Okay, now maybe you're confused why we have n+1. Okay, so we are only accommodating for the overflow bit. Okay, so we've seen earlier that from our previous example, no? Now, if we go, if there's an overflow bit, okay, it will, from a 4-bit binary addition, okay, there's a tendency that you will go on a 5-bit sum, okay, because of the overflow bit. So we will accommodate that, and we go for an n+1 length for element array C. Okay. Now, this is the exact instruction on how, or algorithm on how to do binary addition. Okay. So when you can actually implement this on Python if you would like. Okay. But let's just run through it so that we can see if this algorithm is correct, if it will produce us the correct output. Okay, so in order to do that, okay, we'll just use the same example as the previous slides. No, so we have these two numbers. We have 1011 and 0110, which is A and B, okay, as our input. And for the sum, okay, we have an array C. Okay, so let A, that's the first step. Okay, we assign an array of length n to A. Okay, so we assign this array to length A, to array A. We assign this array to array B. Okay, so in this case, ito na yun. Okay, we assign this array to A, we assign this second array to B. Okay, and then we have an empty array C, which is of length n plus 1. Now, for the carryover bit, okay, we assign a variable which is initialized at 0. Okay, so our first value for carryover bit is 0. Now, for our loop, okay, I'm pretty sure you're familiar with loops. So here we start at n minus 1, okay, to 0. So we start from the rightmost bit going to the left, okay? And in case you're wondering why it's n minus 1 and not n, okay, if you recall in array that our indices start at 0. Okay, so it's not really 1, 2, 3, 4. Even though it's 4 bits, it's actually 0, 1, 2, 3. So the end or the rightmost bit is actually at index n minus 1. In this case, it's at index 3. Okay. So far, so good. Clear pa ba? Or are there any questions at this point? Okay pa. All right. So let me know if you need a break or a timeout, and or if you need me, if you want me to repeat some of the examples. So yeah, and then I'll do it, of course. Okay. So again, so this for loop indicates that we are starting from n minus 1, which is the rightmost bit, going to 0, which is the leftmost bit. Okay. So now our carry is initialized at 0. So we can just visualize a 0 here. Okay. So the first one is we need to add the sum. We need to come up with a sum variable, which adds the A at that index and B at that index and the value of carry. Okay. I don't need to write this down pala because I prepared it in the slides already. Okay. Ito yung carry natin na variable. Okay. Now we add these three. So it's 0 plus 1 plus 0 is equal to 1. Okay. Now we have these two, we have lines 7 and 8 here. Okay. These lines 7 and 8, okay, for programming languages, as I've mentioned previously, that their default setting or notation is decimal. So there's no, unless we use the native packages that, let's say, Python has to convert binary decimal to binary, okay, then you can use that, okay, unless if a programming language doesn't have those libraries, then we need to, again, come up with a formula or a process in order to convert the decimal to binary. Okay, so in this case, if you recall our decimal to binary procedure, okay, where we use integer division and we look at the remainder, okay, so it's the same case for lines 7 and 8. Okay, so the modulo here, or the percentage sign, we call it modulo. Okay, that means we are getting the remainder of the integer division of sum and 2. Okay, so we do integer division. So 1 divided by 2. Okay, so our first sum here is 1. Okay, equals 1. So if we do 1 divided by 2, the answer is 0, remainder 1. Okay, so now what this is saying, what line 7 is saying is that we write down sum modulo 2 at the rightmost bit of array C. Okay, so the modulo is 1. So we write down 1 here. Okay, and then line 8 says that our carry is now equivalent to sum divided by 2, okay, which is 1 divided by 2, integer division. That means it's 0. Okay, so now our carry for the next iteration is equal to 0. Okay, gets ba yung 7 and 8?
Sir.
Yes.
I don't really understand 7. Where did the I plus 1 come from?
Okay, sige. Let's start with the I plus 1. Remember that our length for array C is actually n plus 1. Okay, so if our initial n is 4, okay, since the length is 4, then that means our C will have okay, I'll just put it C underscore n will have 5, right? So in this case, if we go n minus 1, we are pointing at index 3 for A and B. So 0, 1, 2, 3. But for array C, since it's n plus 1, we actually need to point at 0, 1, 2, 3, 4. Okay? So we actually need to point at index 4 to indicate the rightmost bit of array C. That's why here, okay, instead of just C of I, we use C of I plus 1. Okay? Because if we use C of I, then we will be pointing at index 3. So it will write 1 here instead of at the rightmost bit. Okay?
Okay, thank you, sir.
Does that make sense? So we just used I plus 1 because again, meron tayong extra bit on our array C. So they are not on the same lengths. That's why. Okay. But the point here is just to look at the rightmost bit of array C. So since it's n plus 1, we go for I plus 1 here. Okay. Bakit 0 ulit si carry? Okay. Again, we are doing integer division. Okay. That means if you recall the long division that we are all doing when we are in grade school. Okay. So 1 divided by 2. This is 0. 0 times 2 is 0 divided by 1. 0 plus 1 is equal to 1. So this is the integer division. And this is the remainder or the modulo. Okay, so this pertains to line 7. This pertains to line 8. All right. Jani, is that clear? Okay. Okay, so we are doing integer division in this case. So now let's proceed. So now we know that the carry for the next iteration. So now we move from n minus 1 to n minus 2. Okay, so from index 3, we move to index 2. Okay, so now our carry variable has a value of 0. Okay, so we can still proceed with the sum. So 0 plus 1 plus 1. Okay, again, by default, programming languages would use decimal notation. So just put it as 2 for now. Okay, so the sum here is equal to 2. Okay, so now our modulo here, okay, itaas ko lang dito wala ng space. Okay, let's proceed with the integer division. So sum divided by 2 is equal to 1. Sum remainder 2 is equal to 0. Okay, so in case you're wondering, so we go again with the long division. 2 divided by 2 is equal to 1. 2 times 2 is 2. 2 minus 2 is equal to 0. This is the integer division. This is the modulo or the remainder. Okay, so exactly the same thing. Okay, so now we write the modulo, okay, at array C. Okay, and we assign the value of the integer division at this point on the on our variable carry. Okay, so now we have 1 here at the carry. So far, nakikita nyo na ba yung process on how it flows down? Okay, so if we do the same thing, we get the sum at this point equals 1 plus 0 plus 1 is 2 again. Okay, so let's just use the same representation here. So it goes, we write 0 at array C, and then we carry over 1. Okay, so the sum here, again, is the same, 2. So we write 0 okay, at array C. Now we have a carry 1, okay, here. Okay, there should be a carry 1 at this point. But at this point, okay, we have already reached index 0 for arrays A and B. So that means we will now fall out of this loop. We will now exit this loop and move here to line number 9. Okay, at line number 9, it simply says that the first index or the first element of array C, which is at C0, we assign the value of the carry variable. So if we do that, we have 1 here, and then we return the value of C as the sum of these two integers. Okay? Is that clear? Okay, so we just did a paper debugging of this algorithm, and we can see using even our own examples from the previous slides, okay, that we will arrive at the same answer, at the correct answer using this algorithm. Okay. Now, this algorithm, okay, as you can see, we are using some weird notations maybe that you haven't seen, okay, such as the arrow sign to the left. For the for loop, it's pretty generic. So we just indicate the start and the finish. What else? Wala namang other special thing here, okay? But this thing that you're seeing here is actually what we call a pseudocode, okay? It's used to describe algorithms using high-level language that abstracts programming structures. So we did not indicate any Python library. We did not use any C# or C++ library. Okay. And we even used an arrow sign to represent assignment. Okay. So our usual C equals 1 will become C left arrow 1 when we write pseudocodes. Okay. That is to abstract it from programming specific notations so that we can implement them on a different programming language. Okay. If you have experience doing R programming, they are not using equal sign as assignment. They are actually using arrows for variable assignment. And maybe if someone comes up with another programming language, they would use a different sign for assignment. Then you need to use that basically. So if we don't have an instruction that is applicable to any programming language that does that, then it will be much difficult for anyone to implement those algorithms. But in this case, our pseudocode eliminates that problem. Okay, so we just made it clear na, let's be clear, basically we use these notations to indicate specific operations. Okay, so now in this pseudocode, okay, we can still see the same algorithmic structure. Okay, we have our computational problem here, which is our input and our desired output. We also have the instance of the problem or the inputs that the algorithm needs to basically do its task. Okay, or let's say the ingredients to your recipe. We have the algorithm here on the actual steps that needs to be done to perform the transformation of input into output. Okay, so that's the algorithm from lines 5 to 10. Okay, now in writing pseudocodes, we have various notations. Okay, you can use decision structures like if and like if else. Okay, switch cases. So it's also similar to an if else statement. You can also use loops. Okay, so for example, here we've used for loop as to iterate, to do the iterations from each element. Okay, so you can also use while loops. Ano pa ba ibang loops na meron? You have for loops, you have do while loop as well, and so on. Right? So from expressions, okay, it supports standard math operators from plus, minus, divide, multiply, modulo for the remainder, and even curret for the exponent or the power. Okay. Relational operators, if you want to compare, if you want to do some comparison, you can use greater than, less than, greater than, equal, or equal and not equal. Okay. The reason why assignment is used, we use left arrow for the assignment Okay, it's because so that we don't confuse ourselves with a comparison operator. Okay, so if we're simply comparing, if A is equal to B, we use the equal sign. If we want to assign, let's say 1 to variable A, then we use the left arrow to indicate that. Okay. We can also use Boolean operators and or not. Okay, and also array indexing. To refer to the index of an array, we use square brackets. Okay. Now, any questions? Okay, any questions? The class, none from Jenny. How about the rest? Okay pa kayo? All right. Sige. Now let's proceed. Okay, so again, let's go back. Now we are going into how do we look for algorithm runtime. Now that you at least have a glimpse or you know how a pseudocode looks like, how do you actually get the runtime for that? Okay, so in order to do that, let's again do it by example. Let's say you're looking for your x in an array. Okay, so we have this function or module or um, library, let's say, which is a search, and it accepts an input A and the query X, the one that you're looking, the one that you're looking in the array. Okay, so if we have, so imagine you have an array and you have to search through all of that with you have to search, you have to look at each element to search for element X. Okay, so let's break down the cases. Assuming that the X is located at the very first index of uh, of the array. So it's the first element of array A. That means we did one check. Okay, we just check if A of 0 is equal to X, then it's true. Okay, because X is located at A0. Then we can assume that this is the best case because we arrive at the answer um, at the soonest time possible. Okay, we just did one check. Okay, and we got the answer right away. So good. So it's very easy and very feasible. Okay. Now, in case that X is located at the end of the array, okay, and we did not define the length here, so we can assume any length n at this point. So how many numbers of checks are we expecting? Ilang check operations yung expect natin in this case? If X is located at the end of the array, that means our algorithm has to do how many checks? N number of checks, right? Correct. So our algorithm has to go through all of those elements until it arrives at the last element and say that, okay, X is at the last element of array A. The same case as when X is not in the array. Okay, you still have to go through all of the elements just to say that X is not in the array. Okay, so again, this is we can say that this is the worst case of the algorithm. Okay, so because if our n is too large, then that means that our runtime will also be too big. Okay, to be feasible enough. Okay, so if you remember my quick example earlier, if I ask you to find somebody on Facebook and I ask you to lay down all the users, okay, and scan through all of them, okay, it's the same example here. So we are searching for an element across an array. Okay, so now the algorithm runtime here is the number of operations that are executed. Okay, so here our execution here is simply to check if the element at that index is equal to the query. If yes, we return the query. If are the index, if not, then we move to the next one. So that's the simple operation that's happening here. Okay. now from in terms of improving the runtime, okay, so if we improve the worst case time, okay, so instead of going from n, let's say we reduce it somehow, then we can also reduce the best case time. So from improving from the perspective of improving an algorithm, we can simply look at the worst case scenario and improve that, okay, or count the operations at the worst case, okay. So we don't need to deal with the best case again, because if we bring down the worst case, we can also bring down the best case, so make it more efficient as well. So we simply have to rely on the worst case scenario as the algorithm runtime for that algorithm, okay. Now, what are these operations that we're talking about? Ano yung kailangan natin bilangin? Okay, we have the primitive operations that a computer or a machine understands. Okay, first of all, the assignment. Okay, you've seen the I equals 1. Okay, or kanina array equals 0 or array left arrow 0. Okay, that's an example of assignment. We also do calculations. So any arithmetic operations done in the variable, okay, that that is also counted as a primitive operation. So kanina yun yung sum plus a of I plus b of I plus carry. Okay, so there are two arithmetic operations going on in that sum formula. Okay, we also do logical comparisons. So if your algorithm does a is a greater than b, okay, or if statements, if a is greater than b, then that that condition, okay, performing logical comparisons will also be counted as an operation. Okay, indexing and other data structure access. Okay, if we go from a of I, okay, that's also counted as one operation. And if we return a variable, return c, or we call a variable, let's say I is equal to n plus 1. So we are calling the variable n, and that is also counted as an operation. Okay, so these 5 operations, we are going to count them and to come up with the algorithm runtime. Okay, again, for examples, if we have I assigned left arrow 3, we count it as one operation, which is one assignment. Okay, so if we go for array indexing, if we assign 3 to a of I, okay, that means we have 2 operations. We have indexing, where a of I is coming from, and we also have the assignment, okay, the assignment operation. Okay, so and if we go for a more complex example, let's say a for loop. Okay, so this is our for loop. We go from right to left. So we can break it down first into initial assignment, and then to the comparisons and to the increment and the exit condition. Okay, so paano nangyaring ito yung number of operations for this for loop? Okay, our initial assignment would be an I assign n minus 1. Okay, so we know that we have 2 operations here, okay, which is the calculation for the subtraction and the assignment. Okay, at some examples, you might be looking into the n as well, because that is also a return or call. Okay, but to simplify things, I just look at subtraction and assignment here. So we have 2 for the initialization, for the initial assignment. Now for comparisons, okay, it will compare whether I has reached 0 or not. Okay. Okay, because that's the exit condition. Okay. So if it's still greater than or equal to 0, okay, then it will proceed with the loop. Okay. If it goes less than 0, then it will exit the loop. Right? So this is performed n times depending on the length of your array or length of your data size. Okay. And we will also, it will, the for loop will also perform another operation. Okay, so even if the index is greater than equal to 0, ito yung gagawin niya. Okay, but it will still perform a comparison for index equals -1. Okay, because this will indicate the exit from the loop. Okay, so it will still perform comparisons from index equals n-1 to 0. Okay, but it will also perform comparison at index equals -1. So that's the additional one here on the comparison. So n plus 1. Okay. Okay, sige. Let me repeat that. Bakit n? Because it will we will walk through from index n-1 down to n0. So this has the length of n. Okay, so that means that this comparison statement will be performed or will be executed from n-1 to 0. Okay, that's n times. Now, in order to exit that loop, okay, for the loop to understand, for the program to understand that okay, it's exit time, it still needs to perform additional comparison at index equals -1. Okay, so pagdating sa -1, that means okay, we gotta go out of this loop. Okay, but that's still one operation. That's why our entire comparison is an n plus 1 operation. Okay, now the last one is the increment. Okay, so we go from I equals I minus 1. Okay, so this increment will again run from n-1 to 0. Okay, and na-indicate here that we have 3n because we have subtraction, we have the assignment, and the reference to or the calling of variable I in this loop. Okay, so we have 3n here. Okay, any questions at this point? Okay, clear ba yung breakdown ng for loop into these different operations? Or at least it's making sense in your heads. Okay, makes sense for Jenny. Sort of. Okay, sige. We'll have more examples later on, but just understand that for loops, these are the different operations that are happening. Okay, even though if you use a switch case, let's say for conditions, you're still performing if conditions at the back end, okay, or behind that. So you can still break down the switch case into multiple if-else statements. So you can do that as well. Okay, so what we're seeing here is that for each of these operations, we count them as one operation. And the main assumption here is that each of these operations are performed at 1 unit of time. Okay, so we don't define if it's milliseconds, if it's seconds. Again, the reason is each machine may have a different calculation or different ways to come up with unit time. Okay, so maybe one is using milliseconds, another machine would use a microsecond, and or even smaller than that. Okay, so we don't know, but what we're assuming here is that one operation is counted per unit of time. Okay, so that's why we can rely on number of operations to look for the algorithm runtime. Okay. Okay, now let's look again at our previous algorithm or previous pseudocode, which is the binary addition. And let's try to count the operations here. Okay, so at first we have an assignment, which is A. We assign an array of length n to A. That means we have one operation here. Same for B, the same for C, and the same for carry. Clear so far? Makes sense pa, no? Now, earlier we already computed for the number of operations for the for loop, okay, which is 2 plus n plus 1 plus 3n. Okay, so copy na natin yan. Now, here, how many operations do we have? So we have one index, two indices. So that's 2. We have 2 operations. So that's a total of 4. We have one calling a variable carry. That's 5. And then we assign it to variable sum. So therefore, we have a total of 6 operations. Okay. So since we have 6 operations, but it is inside the for loop, which allows us to scan through all of the elements. So that means you will do the 6 operations n times. So the number of operations here would be 6n. Okay. Is that clear? Yes. Okay. So one more time. So we count again the number of operations for line 6. We have index here for A of I and B of I. So that's 2 operations. We have 2 additions. So that's another 2. We have carry, which is calling the variable carry that was initialized. So that's 1 operation. And we have assignment here, which is another operation. So we count them. So 1 plus 1, 2, 3, 4, 5, 6. Line 6 will have 6 operations in total. Okay. But since it is in the for loop that will scan through all of the elements, through all n elements, that means this 6 operations will be performed n times. That's why we arrive at 6n for a total number of operations. Okay. Now for line 7, we do the same thing. So we have operation here. So that's 1. We have a calling of variable. So 2. We have assignment 3. Okay. And we have the indexing at 4. So this is a total of 4 operations. And this will happen n times. That's why the total number of operations for line 7 would be 4n. Okay. Now for line 8, we count the number of operations again. We have sum, calling. We have the calculation. Okay. And we have the assignment here. So we have 3 operations, which will run again on n elements. That's why we have 3n. Okay. If you're wondering but hindi natin binilang sa carry, we're not exactly calling carry at this point, but we are actually assigning a new value to carry. So we don't count carry as an operation here. Okay. Now for the last one, we have index, we have assignment. Okay. So that's also 2. You can also say it's 3. Okay. Because we are calling the variable carry. Okay. You can also proceed with 3. Okay. But in this case, let's just call it 2. And the return is 1. Okay. Returning of variables will be 1 operation. So we just simply add all of these and we arrive at a 17n plus 9. Okay. So once we add them, okay, we can see that the time, our algorithm runtime, is a function of the input data, the size of the input. Okay, so we use the T of n as a notation for our runtime. So this means that our algorithm here runs at 17n plus 9 operations, or 17n plus 9 runtime. Okay, so what does that mean now? Okay, we are moving into the algorithm runtime called the big O notation. Okay, so the big O tells you how fast an algorithm is by comparing the number of operations. Okay, so we are counting the number of operations, and based on that, we can say, okay, this algorithm will run faster than the other algorithm. Okay, what the big O basically does is assign that function, the T of n, into a class or category of efficiencies. Okay, And overall, we can describe the runtime in terms of the size of the input. Okay. So from an example perspective, okay, let's say we have two search algorithms, the simple search and the binary search. If we if we do simple search on 100 elements, okay, on layman's term, okay, without using the algorithm, it might take 100 milliseconds. But for the binary search, a different algorithm would take 7 milliseconds. Okay, if we run 10,000 elements, okay, it might take 10 seconds or 10 operations. Okay, and then it would take simply 14 milliseconds even for binary search. So it's a smaller runtime compared to the other. If we go for 1 billion elements, okay, a simple search would run for 11 days, while for binary search, it will still run on 32 milliseconds. So from here, we can classify that the simple search is a very inefficient search method, while binary search is a more efficient one. If you remember, if you also recall during our first meeting where I presented this graph, okay, comparing different algorithms. So we can say that algorithm 2 is not an efficient algorithm because it grows the runtime faster than the rest of the algorithm. So linear 1, algo 1, which is the blue, uh, grows linearly. Okay, algorithm 2 grows quadratically, while algorithm 3 and algorithm 4 grows logarithmically. Okay, and we will explain it. I'll also explain it later on. Okay, so how do we write the big O? Okay, it's very simple. We have the big O as a function of the number of operations. So of an O of n. Okay, so now what are these categories we're referring to? Okay, these classes or categories of efficiency. Okay, so first we have the constant function. Okay, so if your runtime is equal to a constant, then we can say that it's an O of 1. Okay, if it's a logarithmic function, which means that our runtime is a log n, then our category would be an O log of n. Okay, so we go for linear. Has if its highest order is n, okay, then it's an O of n. Linear arithmetic is n log n or n times log n. That's O of n log n. A quadratic function is an O of n squared. Cubic function is O of n cubed. Exponential function is O of a constant raised to n. And factorial function is an n factorial. Okay. Now this again is in the order of best to worst. Okay. So if you find, let's say, your algorithm at O of n squared, then you would want to make it a little bit more efficient and move it to either a linear arithmetic function or a linear function or better logarithmic function. Okay. So if we are looking at the graph or the growth of these algorithms, it's similar to the graph I've shown earlier. Okay. So we can see this type of movement. So log n, okay, as the input size grows, okay, the runtime reaches a certain asymptote or certain limit, okay, but it doesn't exceed beyond that. Linear growth means that as the input size grows, okay, the runtime grows at a proportion. Okay, we also have the n log n and quadratic, and for n factorial, it's a very steep growth. Okay, just a few additions into the inputs data set, input size. Okay, tumataas lalo yung runtime niya. Okay, so now this is our previous algorithm, and we arrive at 17n plus naging 10. I think I did some changes before. I'm not sure what exactly. Okay, so 17n plus 10. Actually, we don't need to look at the 10 anymore. What we need to do is simply to look at the highest order term. Okay, so here our term with the highest order is 17n. Okay, so we drop the coefficient and we assign it to category O of n. Okay, so even let's say if you have another algorithm for binary addition and the number of operations would be 5n plus 100, then that still falls under an O of n category. Okay, so again, we just simply have to look at the term with the highest order. Okay, the term with the highest order means the term with the highest exponent. Okay, so let's say we have as another term here, which is 3n squared plus 17n plus 10. That means our highest order term would be 3n squared. And we drop the coefficient, then that brings the runtime at on squared. Okay? So this is more of the categorization pa lang, ha? So, okay. So what this indicates is that this process of adding binary depends on the length of the input arrays, which is n. Okay, and it grows at a linear proportion. Okay, so if in case we have n equals 4, okay, then it grows the same if we have n plus equals 5. Okay, so the runtime will grow linearly at a proportion. Okay, so the growth between n equals 4 to n equals 5 is the same as the growth from n equals 100 to n equals 101. Okay, so same lang yung growth nila because it's linear. So we can expect that here, the more numbers that we are adding, the slower our algorithm would be. Okay, at an equal rate. Okay, so that's our thinking here. Okay, so now we know that adding binary addition, it's a linear algorithm or linearly growing algorithm. Okay, let's look at a different type of code. Okay, so what if I asked you to print the elements of a 2D array? So very simple. We have an input of integers. We have an array of integers with size n of n. So it's a 2D array. Okay, and we want to print all the integers on one line. So nag-print lang siya, nag-print. Okay, so we have the input here at a. We assign an array of size n of n to a, and we have 2 for loops. Okay, basically, so we run it on each rows. Okay, and then we also run it on each columns, and then we print a of ij for each iteration. Okay, so in this case, we have our first initialization, which is I equals 1, I equals 0. We have the n plus 1 comparisons. And our 3n here is I equals I plus 1, the iteration or the increment. Okay, clear so far? Paano nangyari? Okay, so if we simplify this, we arrive at 4n plus 2. Okay, so this for loop is the same as this loop in essence. So it's also 4n plus 2. Okay, but now we need to look at here. So look at this point in a way that the for loop is running under a for loop. Okay, so this for loop, this 4n plus 2 will actually run 4n plus 2 times. Okay, so if we compute for this one, okay, so ano ba to? This means 16n squared plus 16n plus 4. Okay, so that's the number of operations simply by going for a nested loop. Okay, and then we go for print. Okay, so the printing will happen on n times n times n multiplied by n times. So that's n squared. Okay, so if we add all of these, we arrive at 1 plus 16n squared plus 16n plus 4 plus n squared, which is equivalent to 17n squared plus 16n plus 5. Okay, so again, what do we need to do to assign a big O category? We look at the term with the highest order or highest coefficient, and we drop the coefficients, and we arrive at O of n squared. Okay, so this is a quadratically growing algorithm. Okay, now what if our input is, instead of a square array, which is n of n, what if there are different elements? Okay, so it's an n times m. Okay, so instead of n by n, we have n times m. Okay, so we simply change the number of columns from n to m. Okay, so that means that we will run the algorithm at an n times m operations. So our big O can be O of n times m. Okay, but it's still the same as a quadratic function. Okay, so if you probably look at some algorithm runtimes online, some of them might actually use this notation to indicate quadratic growth. Okay, so n, instead of n squared, they will use n of m, simply because the input size is different. So here we have a square array of n of n by n. Now here we have more of rectangular array, or more of a generic array, n by m. Okay, so it will still run through all of the elements of all of the n by m elements. So it will still be O of n times m. Okay, in case you look up on Google on this, and then you find other notations for n squared. Okay, the same way as linear. Okay, so let's say our O of n. Okay, some of them would actually put O of n plus m if our two integers have different sizes. Okay, so if we go back here, the previous slide. Okay, our two integers have the same length. They have the same n bit integers. Okay, so if one of them has a different length, let's say this is m. Okay, then that means it will still, the algorithm would run at an O of n plus m, but it will still be considered as linear. Okay. All right. Any questions so far? Okay, none so far. All right. Now going back to our big O notation. Okay, if we have different runtimes. Okay, so let's say we have 2n plus 3. We have 4n squared plus 5n plus 2, and we have 5n. Okay, we can say that the runtime 1 and runtime 3 would fall under the same category, even though they have different coefficients. Okay, we have 2, we have 5, but they are still both O of n. Okay, so we know that if we increase the input size, it will also increase the runtime at the same growth. Okay, at a certain proportion, and we know that the second runtime is under a separate category, which is of n squared. Okay, because again, we look at the term with the highest exponent, okay, and drop the coefficient, and we arrive at n squared. So it's an O of n squared. Okay, how do we standardize the big O notation? Okay, so for example, if we have the same loop, right? So for I equals 0 to n minus 1, and then we assign 0 to all of the elements of the array. Okay, if we are only counting for the assignment and indexing, okay, we arrive at 2n. Okay, this one. So indexing and assignment, it will happen on 2n operations. Now, if we include the loop
현재로선 돕기 어렵네요.
Okay, if we include the loop here, if we count the loop and the assignment, the runtime may grow at 4n plus 1. Okay, but if we also include the comparisons here, the I less than equal to in minus 1, okay, and also the increment equals I plus 1. Listen natin. Okay, if we still count on these increments, it will grow at 5n plus 2. But again, using the example before, okay, these three runtimes would still fall under the same category, which is O of n. Okay, that's why kanina, there might be some discrepancies in terms of counting. Okay, so minsan 1, minsan 2, depending on the assumption, but still we can disregard them and just automatically say that the algorithm is an O of n algorithm. Okay, now this language, this O of n, if you have O of n squared, okay, that standardizes the language on the performance of an algorithm. Okay, so if we look at certain literature or other references, it will mention that this algorithm will run on O of n squared. This algorithm will run on O of n log n. This algorithm would run of O of 1. Okay, so now you would have an idea that, okay, this is just a constant. Okay, this one grows quadratically with any input size. This one is a linear function. So if you're using, let's say, a library in Python, let's say a NumPy or Pandas library, okay, they actually indicate in their documentation kung ano yung runtime. So if you are wondering why your programs are slow, maybe you would want to investigate ano yung runtime ng algorithm behind that module or behind that library. Okay? All right. So let's wrap up the session. Okay, so again, algorithms can be expressed as a pseudocode. So it's an abstraction from programming language specific structures. Okay, so we're using high-level language so that we can implement this across all programming languages available. Okay, at the same time, we can perform counting of operations, counting of number of primitive operations on the pseudocode. So we rely on the core operations going on in the algorithm. Okay, so algorithm runtime can be measured by counting the number of operations, and it's very dependent on the size of input. So we've seen, at least from the examples earlier, na we have linearly growing algorithms, we have quadratically growing algorithms for nested loops. Okay, so a linear search would be a linear growing algorithm, okay, and so on. So all of these things can be classified under a big O category. Okay, so let's say our runtime was 4n plus 2. That means it's an O of n category. Or in the case of our nested loops, nested for loops, it's an n times n or n squared runtime. So it's an O of n squared big O notation. All right. So if there are no other questions, okay, that ends our session for today. Let me just give a few more probably examples or references on Canvas when I upload this session. Okay, so just to add to the learning in case some of my explanations weren't clear. Okay, so either you can refer to other materials, or I can also share some materials regarding counting of operations and the big O notation. All right.